Okay, so hello everyone, welcome to my channel. Today I'm gonna start a series on numerical methods, which is something that I'm very interested in. And what a better way to start with a root finding method, uh, the very classic and well-known Newton-Raphson method, which is used to solve equations of the type f of x is equal to 0. You can actually extend this method to solve systems of equations, which we are going to do in the future, but let's stick with a simpler case for now. Now, in any iterative numerical method, you want to start with an estimate of the solution, denoted by xi. And with your numerical method, you want to update that estimate to compute a better one, xi plus 1. And you do this in an iterative fashion until you reach your desired accuracy, for example, 4 decimal places. So, a very useful tool in all of numerical analysis are Taylor expansions. You're going to find them everywhere, which you can see the Taylor expansion for a general function f of x around a point A is denoted by this expression. So if you substitute xi plus 1 for x and xi for A, you get this expression plus some higher order terms. If you omit the higher order terms, or as we say, if you truncate them, you can drop the equal sign and get an approximate sign. And now you have this expression, which is approximate because you drop the higher order terms. Now, since x of I plus 1 is a better estimate of xi, you can assume that f of xi plus 1 will be equal to 0, which results in this expression, which you can then solve for xi plus 1 to arrive at the Newton-Raphson method, which is very nice and compact, and you can code it very easily. Okay, so let's now demonstrate the method in a programming language. Here I'm going to use the C programming language. You can of course use any language you want. So let's get started. Let's include the standard input and output header. We will also need the math.h header and int main and return 0. We will first need to somehow define our function f, which I'm going to do here. We will take an input x and return our desired value. Let's choose f to be x squared minus 2, which when we set it equal to 0 results in x is equal to the square root of 2, which is a nice example. So POW here stands for power, so x squared minus 2. So when we solve, we need to get x is equal to the square root of 2. We will also need the derivative of that function f prime, so let's code that right now. That's going to be 2 times x from calculus. Let's add these functions at the top, which is a good practice in C. And let's start coding the main part. So let's first write the number of iterations that our method will use. Let's say 5, an integer. And then we will write our initial guess. Let's say is 0.5. And then we will start a for loop for the number of iterations. And we will update x with each iteration. f of x over f prime of x. And let's print the result in the console. Let's use 4 decimal places, for example, and a new line. And we can now compile and run. And we can see that we get 1.4142, which is very close to the square root of 2 after 4 iterations. Now let's see what happens if we enter more decimal places here in the printf function. Let's say I choose 20 and I run this again. I get this result after 5 iterations. If I compare this result with the scientific calculator of Windows, I can see that I'm correct up to this decimal place. So I've got these decimals correct. The other ones are wrong. So let's increase the number of iterations and see what happens now. After 10 iterations, we get this result. If we compare with this scientific calculator now, we see that we are correct up to this 5 here. These are 15 decimal places. Then it's wrong. Let's say I now increase to 15 iterations and run again. You can see that after this iteration, we get an alternating pattern between 951 and 949, which is no coincidence. At this point, round-off error kicks in since we use a double precision number that is good up to 15 digits. So then our method fails. So no matter how many times we iterate, let's say I use 100, you still get the same result. This is an issue in numerical methods. You need to be aware of this. So this pretty much sums up this video. I hope you find this useful. I can elaborate more on future videos on this topic of numerical precision, error analysis and stuff like that. Let me know in the comments and consider subscribing, as this will give me motivation to do more of these videos. Thank you very much for watching.